COA question based upon a pipeline processor. We have been given a processor having 5 stages, and those are instruction fetch, decode, execute, memory access, and the write back, which we are already aware about. Now they have given that each stage of this pipeline except for the execute stage takes exactly 1 cycle. And what about this execute state? It will take more number of cycles depending upon what is the type of the instruction being executed. We have to assume that in the decode stage we merely decode the instruction, so there is no other overhead that is being performed. The register read is performed in the EX stage, execution stage itself, so we did not consider it elsewhere separately. And this EX stage, execution stage, is taking 1 cycle for the add instruction and 2 cycles for the MUL, multiplication instruction. So these are the two types of instructions that will be considered for this question, and they have said that it takes 1 cycle for add and 2 cycles for MUL instruction. So now they have given a sequence of 8 instructions, which is the alternating sequence of add, MUL, add, multiply, add, multiply, add, multiply. So assuming that every MUL instruction is data independent on that instruction just before it, which means this instruction will be data independent of its previous add instruction. This particular information will be useful when we deal with the operator forwarding part. And every add instruction except the first one is data dependent on the MUL instruction, which is immediately after it. So there is dependency between them on the MUL instruction just before it. So this is not after. Both of them are dependent on their before one. Then only will dependency work out. Otherwise, it cannot be dependent on a later instruction. So both this add instruction is dependent on its previous MUL, this one on its previous MUL, and so on, except for this first one. And same thing applies for these MUL instructions as well. Even they are data dependent on their previous add instructions. So this simply means that the data, whatever would be returned by the previous instruction, would be useful for the next instruction to carry out its own processing. They are not independent of each other. The result of the previous stage would determine the result of the upcoming stage or the current stage. So that's what they mean by data dependency over here. And now, given all this information, they have defined what do they mean by a speed up ratio. That also we already know. It is the execution time without operator forwarding divided by the execution time with operator forwarding. So we will have to consider both of these cases one by one. First we'll be dealing with operator forwarding thing without operator forwarding, and then we shall calculate what is the total time required when we perform or when we make use of this operator forwarding thing. Obviously this second concept, which is with operator forwarding, that will take lesser time because we will make use of this dependency concept and the operator forwarding will be applied, so that will take lesser time. And then depending upon them, we'll see what is the speed up we can achieve by using this particular concept. So we have to report that answer rounded up to 2 decimal places in this. So let us calculate both of them separately one by one. So first let us go for this operator forwarding without that. Traced out a tabular representation for without operator forwarding, and over here these are the time units for the stages which we might require, and these are those 8 instructions sequence which we had been given for execution. So we have 5 stages in this processor, which are fetch, decode, execute, memory access, and the write back. And we have to keep in mind that this execute stage takes 1 cycle for add and it takes 2 for MUL instruction. So let us start filling out this table. The first instruction which we are having is the add instruction. So for that we will simply have fetch, decode, execute, memory access, and the write back. Simple. At t equal to 5 it is complete. And coming to the next one, which is multiply instruction, that will start fetching it after the previous instruction has been fetched. So it is fetched at t equal to 2. then it can be decoded while the previous instruction is still executing. But for this instruction to start its execution, we will have to wait until this has written back. So execute for this instruction can only start at t equal to 6. And since it is an MUL instruction, it will take 2 cycles for execution. Then it's memory access and the write back. Now coming to the next one, which is add instruction again. It will be fetched here, decoded over here, but for execution it will wait until 10, then execute, memory access, write back. The next one is again MUL instruction, so it will be fetched here, decode, then execute for 2 cycles, memory access and the write back. Coming to the next, which is an add instruction, that will be fetched at t equal to 10, then decoded at t equal to 13. For execution it will wait until 17, and then this is its execute. It will take only 1 cycle for that, followed by memory access and the write back. Then next we have the multiply instruction. For that the fetch takes place over here. Then this is the decode, execute, 2 cycles for that, memory access and the write back. Next again an add instruction, so it is fetched here, decode, execute, memory access and the write back. Then coming to the last instruction, which is again an MUL, it is fetched at t equal to 20, then decoded at 24, then it will wait for execution till here, 2 cycles for that, then memory access and finally write back. So this completes our sequence of 8 instructions that were to be executed, and we saw that the total time it took for performing this is 30 cycles, because at t equal to 30 the last write back for this last MUL instruction has been completed. So it took us 30 cycles when we used without operator forwarding thing. Now we will also check how much cycles does it take when we use operator forwarding, and then their ratio would help us to calculate what is the speed up achieved. So keeping this 30 cycles in mind, let us now proceed for the with operator forwarding thing, and we'll also perform the same thing over there also. Now moving with the with operator forwarding allowed. Here the only difference which is created from the previous one is that, for example, if the previous instruction has this fetch, decode, execute, memory access, write back, this particular sequence of cycles, then what did we previously do? We fetched the current instruction over here, decoded it when the previous was in execute state, but for executing the current instruction we waited until it finished writing back. We started executing it here. So this wasted 2 cycles. But here when the operator forwarding is allowed, and we also saw what are the dependencies existing. So in this case what we'll be doing is we will start executing the current instruction here itself after the previous one has finished its execution state. For example, if it took, let us say, 2 execute cycles, then what we'll do is we will fetch it after in the immediate next cycle after it was fetched, then decode it in the same way. But here we cannot execute it because the previous is still in the execute state itself. So we'll wait in this cycle and execute it here. Then memory access followed by the write back. So this will save us a few cycles. So let us fill the table in the same way for this one, and let us see how much cycles is it taking. So for the same set of instructions, the first one, which is an add instruction, we will be having fetch, decode, execute, memory access, write back. Then the next one, which is MUL instruction, fetch it here, decode, it will take 2 cycles for execution, memory access, write back. Then for this add instruction, fetch it here, decode, but it cannot execute here because the previous one is still in the same stage. So wait in this and execute it here. Then memory access, write back. Next, which is MUL instruction, fetch it here, decode, execute, it will take 2 for that, memory access, write back. Next is add instruction, fetch it here, decode, cannot execute here, so execute it here, then memory access, write back. Next is mul, fetch, decode, execute for 2 cycles, memory access, write back. Next is an add instruction, so fetch it here, decode, wait here, execute, memory access, write back. Then coming to the last instruction, which is again an mul, we will be fetching it here, decode, execute for 2 cycles, then memory access and the write back. So this completes our execution. And how many cycles did it take this time? It took just 16 cycles, because we were able to write back the last cycle for this instruction, mul instruction, in the 16th cycle itself. So with operator forwarding, it took only 16 cycles. And without operator forwarding, as we previously saw, how many cycles did it take then? It took 30 cycles. So the speedup was defined as the ratio of number of cycles it was taking without operator forwarding divided by the number of cycles it was taking with operator forwarding. So we will be dividing this 30 by 16 and that will be our answer. So it gives us 1.82 or something, whatever it is giving. We have to round it off to 2 decimal places, and that would be the speedup ratio we can achieve given this 5-stage pipeline processor. So this is how this problem will be solved.